Welcome everybody to the lecture by Abdennour Kitouni, who is a researcher at our Division of Mathematics and Physics, the Research Environment in Mathematics and Applied Mathematics at Modern University in Sweden. The lecture will be about properties of n-ary algebras, and it is part of the lecture series on n-ary algebras given by Abdennour. This is a third lecture in the series, and there will be several more lectures given, and there is a website where all lectures are announced, and the link to this is sent in the seminar announcement, and it's placed on our environment web page. So, Abdennour, that's your turn to speak.
Yes, thank you, Sergei. Thank you very much. And welcome, everybody. I'm very glad to see even more than usual of you here. Welcome. So today we will be talking about the properties of n-ary algebras. The previous two lectures were more general about n-ary algebras. Today we dive into this specific type of n-ary algebras, which are n-ary algebras. And we will follow this plan. First, it will be about solvability and nilpotency and all the properties around. And the second part will be about the representations of n-ary algebras. So first I will recall very quickly what's an n-ary algebra. An n-ary algebra is an n-ary generalization of a Lie algebra, that is a vector space with an n-ary multiplication or an n-ary bracket. And that n-ary bracket is skew-symmetric and have a generalization of the Jacobi identity. This generalization follows the ideas that we look at the Jacobi identity as the fact that the adjoint maps or left multiplication operators are derivations of the algebra. So we have this definition. An n-ary algebra is Q-symmetric n-ary algebra satisfying the so-called Nambu or Filippov identity, which expresses the fact that left multiplication operators are derivations. So if I denote the left multiplication operators by Lx1 to xn minus 1, then we have they are defined by the bracket, and one can input them exactly here, and they will be derivations. These operators are also called inner derivations. And again, I will recall the definition of an ideal, since we will be using it a lot. An ideal of an n-ary algebra is a linear subspace, denoted I here, such that the bracket with n minus 1 arbitrary element from A and 1 element from I are always in I. We can also say that an ideal is a subspace which is invariant under all inner derivations. From this, we can also define a more specific type of ideals, which are called characteristic ideals, and which are subspaces that are invariant under all the derivations of the algebra A. A quick property to keep in mind is that if I have n different ideals, then their image by the bracket will also be an ideal. This is a direct consequence of the Filippov identity. So now we move to the topic of our first section, which is solvability and nilpotency of n-ary algebras. The concepts of solvability and nilpotency of n-ary algebras are generalization of those that we know on Lie algebras. The Filippov identity, or the fact that left multiplication operators are derivation, allow this generalization to work and to keep also several properties from Lie algebras. However, this n-ary bracket, the fact that the bracket is n-ary, allows for a whole spectrum of concepts of solvability and nilpotency. Some of them have different properties and different uses also. So now we define those explicitly. We take an n-ary algebra and an ideal I of this algebra. So we define the derived series and the central descending series by the following recurrence formula. For the derived series, which we denote by dr of I, d0 of I is I itself, and then dr plus 1 of I is the bracket of dr of I inserted in all entries. And for the central descending series, we have the first term is always the ideal itself, and then the term r plus 1 is constructed by inserting in the bracket in the first entry or in one entry the previous term cr of I, and then in the remaining entries I put the ideal itself. So these was the definitions that were given by Filippov in his very first article about n-ary algebras, and they are still sometimes called solvability and nilpotency in the sense of Filippov. One thing to notice about before that, naturally we say that the ideal I is solvable if the derived series vanishes at some point. There exists some natural number R0 such that the term number R0 is trivial, and it is said to be nilpotent if the R0 term of the central descending series for some R0 is trivial. So one of the things that are specific to this definition is that if I take an ideal, it will be solvable or nilpotent if and only if it is solvable or nilpotent simply as a subalgebra or as an algebra of its own. Now for this one, notice that we have simply followed the idea that we fill in the bracket completely as we would do for a Lie algebra. So, and the next definition is completely is different. So this one is due to Kuzmin, cited by Kasimov in his article as giving these definitions in a oral presentation, and crediting him for this. So in the same setting, we have an algebra A and an ideal I. And we define the central descending series and the derived series in the following way. The derived series, first term is always the ideal I, and the term r plus 1 will be in the bracket inserting the preceding term dr of I in 2 entries, and I will insert in the remaining entries the full algebra A. And I will do the same for the central descending series. I will only use the first 2 entries, and then as in Lie algebras. So the first is the preceding term, second is the ideal I'm working with, and the remaining entries will be filled by the full algebra. And following this definition, also we say that an ideal is solvable, or solvable in the sense of Kuzmin if there exists some R0 such that the R0 is trivial, or nilpotent if C R0 is trivial. One specific thing about this definition is the following. If I define this kind of product of ideals as being the bracket of the first, then the second, and then fill in with the remaining places with A, then we can rewrite the definitions as follows. So the term r plus 1 of the central descending series will be the term r multiplied by I, and the r plus 1 term of the derived series would be the r term multiplied by itself. This is quite useful specifically for this case of nilpotence, as we will see later. We won't enter into this much level of technicality, but these will be used a little bit in the proofs if one wants to look at the proofs. So those 2 definitions that we just saw would reduce to the same classical definitions on Lie algebras for n is equal to 2, but they will but they are really different and have different properties for n greater than 2. Now, if we look back, for the first one, I used all the entries, and for the second one, I used only 2. So the further generalization would be to imagine that I would use at one time k entries of the n-ary bracket, and it will be something in between those 2 definitions that we have. So we define the k derived series of the ideal I by the following formula. First term is always I, and then here I use k entries. Here for the derived series, I put in the preceding term. Here it should be R, just a misprint. And then the remaining entries will be filled with A. And for the central descending series, I will fill in also the first K, and then the remaining will be A. So first K will I have 1, which is the preceding term of the central descending series, and then K minus 1, the ideal itself, which is a total of K, and then n minus K, the full algebra. And then similarly, we say that the ideal is K solvable, because this K is important, or K nilpotent if there exists some R0 such that the term number R0 of the derived series is trivial, or for nilpotency if the R term of R0 term of the central descending series is 0. So one thing that we should also notice that all these different definitions will be for nilpotency will be the same for any k if we consider as an ideal to work with the whole or the full algebra. So now what one would ask, what is the relation between those k central descending series and k derived series? So we have that all the derived series terms of derived series k plus 1, the k plus 1 derived series, are subspace or subsets of the terms of the corresponding terms of the k derived series. The same goes for the central descending series. K plus 1 is subset of k. And this would mean that if an ideal is k solvable or k nilpotent, then it is L solvable or L nilpotent for all L greater than k. Another property that is not written here is the same as for Lie algebras. An ideal that is nilpotent needs to be solvable in the same sense, in the same central descending series, or for the same index k, so to say. And then now we are talking about these. We define a simple n-ary algebras if we say that an n-ary algebra is simple if it has no non-zero ideal and the bracket of a to in n positions is non-trivial. And an n-ary algebra is said to be abelian if its bracket is trivial. Now we look at abelian ideals. So unlike for the whole algebra, for the ideals, one can have different definitions in the same way as for solvability and nilpotency. So an ideal of an n-ary algebra A is said to be k abelian if the first term of its k derived series is 0. This proposition gives a well-known example of a simple n-ary algebra is that we take an n plus 1 dimensional n-ary algebra. The bracket is defined in the following way, generalizing the cross product on the 3-dimensional space. And this is also as for the cross product algebra is simple. Now I will give another example to see also the differences between those k derived series and k central descending series. So I take this algebra, dimension n plus 1, and the bracket is defined with respect to the basis ei by the following. So the bracket where the element I is missing is equal to alpha I times ei. Now these alpha I are scalars. And this bracket defines always an n-ary algebra. If in the following case, if alpha I is non-zero for I between 1 and k, and then for the remaining alpha i's are 0, then we would have this algebra would be k solvable, but not k minus 1 solvable. This k and this k is the same. So now we present some more properties of these k central descending series and k derived series. So if I take two n-ary algebras and then a surjective algebra morphism F, and then I take an ideal of A, then I have the image of any term of any central of any derived series is equal to the corresponding term for the image of the ideal. Note that since the morphism is surjective, then the image of an ideal will also be an ideal. From this, we can conclude that these k-derived series and k-central descending series are algebraic invariants. That is, isomorphic algebras would have the same, and if two algebras have some terms in some series which are different, then they cannot be isomorphic. For example, of different dimension. Then another property related to this, if we take an n-ary algebra, then two ideals such that second is a subset of the first, I denote by I bar the image of the ideal I in the factor algebra by J. In this setting, if J is k solvable and A in A and I bar is k solvable in A divided by J, then I would be k solvable in A also. And a consequence of this proposition is that if I take two k solvable ideals of a given n-ary algebra, then their sum is also a k solvable ideal. And this allows me to consider the following definition. The k radical of A is the largest k solvable ideal of A if the algebra A is finite dimensional. Or in the same way, it is the radical would be the sum of all k solvable ideals of A. If A contains no k solvable ideals, it is said to be k semi-simple. And we have the property that when I take the factor or the quotient algebra of A by its k radical, it will give a k semi-simple algebra. A little remark here. So since we have different derived series, then we will get different definitions of or different concepts of semi-simplicity, and then different radicals also. For this one, the n semi-simplicity or n radical is the one who is the most, so to say, like the Lie algebra case, as it is the one which is related to simple algebras. For nilpotency, the situation is different as for in solvability. We can only get similar result for k equal to 2, or the nilpotency in the sense of Kuzmin. First, we can prove that if we have the two ideals, then which are 2 nilpotent, then their sum will be also 2 nilpotent. The proof of this statement is far from being straightforward. It will use the algebras, so to say, the algebras of or span generated by left multiplication operators that we talked about earlier, and the properties of those would allow to prove this. And from this, one can also define in the same way as for solvability, the nil radical. But before that, I will show why it doesn't work for other k. So we will take this example. I take the n-dimensional n-ly algebra. The bracket is given by this. So the bracket of E1 to En is equal to E1. This is sufficient to define the bracket, since we are in this very special case of n-dimensional n-ary algebras. So this algebra is not nilpotent for any k. However, it is the sum of the ideals ji. Each ji is generated by two elements, E1 and EI, same index here. And all of these ideals can be easily seen to be k nilpotent for k greater than or equal 3. This means that it is not that we don't know or we cannot prove a similar statement as this one for k different from 2, but we know that such statement is impossible in this case. And so we define the nil radical of an n-ly algebra or a finite dimensional n-ly algebra as the largest 2 nilpotent ideal. So here I don't put in any number, since we have only one nil radical possible to define. And this would be also the sum of all 2 nilpotent ideals of A. And another property of these radicals is that the k radical of A for all k and the nil radical are invariant under all the derivations of A, or what we called earlier, they are characteristic ideals of A. Now we move to talk about the representations of n-ly algebras. First, we give some definitions and properties of the representations, and then we define the basic Leibniz algebra and how it is used together with representations. So first, I will recall the definition of an n-ly module. I will take an n-ly algebra, then an n-ly module over A is the direct sum A with some vector space V. This direct sum would be equipped with an n-ary bracket that I will denote bracket subscript V, such that we have this would be an n-ly algebra, and V must be an ideal of this n-ly algebra, and it must satisfy this. if I take the bracket with V in 2 entries and whatever the rest may be, I will get 0. This can be expressed as saying V is a 2 abelian ideal. So in this generalization, for Lie algebra, we would have this to be an abelian ideal. In here, the right concept to use is 2 abelian instead of n. So, and this bracket by this, these properties of V being an ideal and on top of that a 2 abelian ideal, this definition gives rise to a skew-symmetric n-1 linear map, which goes from A and n-1 to the set of, or the space of endomorphisms of V. And the fact that A plus V is an n-Lie algebra would give us some property to this map. It will not be any random skew-symmetric n-1 linear. And this is what we call a representation. More explicitly, what does a representation look like? It is this. So we take from we begin with an n-Lie algebra and some vector space. A representation is defined by giving this vector space and an n-1 linear map, which would be skew symmetric and satisfying two identities. First, this should be closed bracket. So this bracket denotes simply the commutator in the algebra of endomorphisms of V. So since we had, for the classical case of Lie algebras, a representation would be a homomorphism, a Lie algebra morphism. Here it would be natural, so to say, to look at what is the commutator of two such maps. It turns out to be this sum of rho applied to n-1 elements, and in each term of the sum, this bracket is inserted in a different position of rho. And the second property is this one, where it represents what happens when I take rho with a bracket in the first entry and other random elements elsewhere. So when I have a representation, I can take this subspace of elements X. So here is equal, this kernel of rho is the elements X such that rho of X with any other elements in here would be 0. This is called the kernel of the representation, and it is an ideal of A. If the kernel of a representation is trivial, then representation is called a faithful representation. And if I have any representation, then I can consider this factor algebra by the kernel of rho and define from rho a faithful representation by simply taking the equivalence row bar of equivalence classes is simply row of any representative of these. And the left or equivalently right multiplication on an n-ary algebra defines a representation on its underlying vector space, and this representation is called either regular representation or a joint. In analogy with Lie algebra, we would call it also a joint representation of A. And the kernel of this regular representation is the center of A. So if I go back here, the center would be the elements X, such that the bracket with X and any other n-1 elements is 0. And for representation, we also have a natural generalization of the classical Engels theorem for Lie algebras, which is the following statement. If I have an n-ary algebra which is finite dimensional, I take A star is to be the associative algebra generated by all the left or the right, depending on how one works, multiplication operators on A. And if all of these operators are nilpotent, then the algebra A is nilpotent or 2 nilpotent, and this A star, the associative algebra of generated by left multiplication operators, is also nilpotent in the sense of associative algebras. So now I would point out that we have defined the representations as n-1 linear skew symmetric map. So one may consider a linear map going from the n-1 exterior power of A instead of an n-linear skew symmetric map. And it turns out that this space has some interesting properties. The element of this space are called fundamental objects. So they are basically considered to have n-1 element to hold together n-1 elements of A, and we use the exterior power to express the fact that these objects are skew symmetric, that if I change the order in here, the outcome will change only by a sign, maybe. This is related, of course, to the skew symmetry of the bracket. Those fundamental objects act on the algebra A simply by left multiplication. And we can define the multiplication or composition of two fundamental objects by the following formula. So this X applied to yi is simply the bracket. And I will travel back a little bit, and the commutator of two elements of the representation is exactly this similar sum, with the difference of these objects being the image of by row instead of just these objects. And this is where this comes from. Now this operation has also some properties. So first, it satisfies the Leibniz rule, as in which can be also seen as an alternative version of Jacobi identity. However, this operation is not skew symmetric in general, but the image of these by the adjoint representation is skew symmetric. And third is that this is also another way to say that the adjoint representation is indeed a representation. This is the first, expresses the first condition for add to be a representation. So this space of fundamental objects, which we shall denote by L of A, together with this multiplication, is a left Leibniz algebra, and it is called the basic Leibniz algebra of the algebra A, the n-ary algebra A. It is of course possible to define everything for those who want right Leibniz algebras. Simply here in this, taking right multiplication, and when I multiply these, it will be the object on the right that will act on those, on the different elements of the left one, and not the other way around. And one can get a right Leibniz algebra which has exactly the same property and fulfills exactly the same role. The basic Leibniz algebra is in general not skew symmetric, but it will be skew symmetric if the center of the algebra A is trivial. And its image under the regular representation is always a Lie algebra, since it has this Leibniz rule, which is conserved by regular representation and skew symmetry. We can also use these fundamental objects to rewrite the Filipov identity this way. So this is a different notation that cause a little bit of mistake. So this point is exactly the bracket of in here, and in the other one is the action. And with this basic Leibniz algebra, we can define a representation, or equivalently an n-ary module over A, as a representation of the basic Leibniz algebra, or for modules we can say a Leibniz module or, over L of A, with the extra condition number 2 in here. So this one, as when we work with the basic Leibniz algebra, this one is always satisfied. We need to have this extra one. Now I will give a little bit some examples on the basic Leibniz algebras. So first we have this algebra A n plus 1, which is the n-ary generalization, so to say, of the vector product. If one wants to calculate or compute the basic Leibniz algebra of this algebra, we will get an algebra which is isomorphic to the Lie algebra SO n plus 1. Now I take another example. So here I take a ternary three-dimensional algebra on which the bracket is defined by this. The bracket of E1, E2, E3 is equal to E1. The basic Leibniz algebra would be generated by these three elements. Only three here because of three-dimensional and skew symmetry. So we will have a three-dimensional Leibniz algebra, which turns out in this case to be a Lie algebra. The multiplication will be defined on these generators by this formula. So U1 and U2 together gives 0, U1, U3 minus U1, and U2, U3 minus U2. Now I move to another example. Now I take a five-dimensional ternary Lie algebra on which the bracket is defined on some basis by the following. So here I have E1, E2, E3 is equal to E4. This is similar to the algebra of the cross product, but I have an extra element which is not here. So this algebra can be regarded as a kind of ternary generalization of GL2. So in this case, when we begin with a five-dimensional ternary algebra, the basic Leibniz algebra would have dimension 10. And in this case, since the center is not trivial, we will have E5 as an element in the center. We would expect this basic Leibniz algebra to be non-skew symmetric, and it's indeed what happens. I won't give all the calculations in here, but only what's of interest to us. So when I take those two generators, E1 wedge E2 and E3 wedge E5, in this order gives me E4, E5, and in the reverse order gives 0, which clearly shows that this algebra is not skew symmetric. So thank you very much for coming. This is all what I have for today. Thank you very much.